Hello everyone, welcome to my second video of the semester where I'm going to be talking about what I learned. Today we are diving into the critical concepts covered in chapters 7 through 12. In the previous chapters we looked at the basics of hardware, and now we are shifting gears to look at the bigger picture, or how we actually design enterprise networks, how we segment them for security, how we connect them across the world, and finally, how we protect and recover them when things go wrong. So first, let's jump into the evolution of network architecture. So chapter 7 focuses on how network topology is changing to meet modern demands. We have two major shifts here. First, if you look at this diagram, this is a spine and leaf architecture. Traditionally, we use a three-tier design with core, distribution, and access layers, but modern data centers have shifted to this design. Notice the mesh connections, which are right in here. Every switch on the bottom leaf layer connects to every switch in the top spine layer, and I want to highlight why we do this. Modern servers talk to each other a lot, so we call this east to west traffic. By using this mesh, traffic is always the same number of hops away, which makes latency predictable and significantly faster than older designs. And now if we look at the diagram on the right, this represents software-defined networking, or SDN. In our traditional switch, the brain, or control plane, and the muscle, or data plane, are in the same box. SDN changes that. See the controller layer in the middle? We have ripped the brain out of the individual switches and centralized it. The controller uses APIs to push instruction down to the infrastructure. This means if I need to update a security policy across 500 switches, I don't log into them one by one. I write code once in the application layer, and then the controller pushes it everywhere instantly. Moving on to chapter 8, we deal with segmentation. So we segment networks to limit the blast radius. If one computer gets infected, we don't want the whole network to go down. So this diagram illustrates a classic setup, which is called router on a stick. You might imagine that like PC1 is the HR department or VLAN 10, and PC2 is the engineering or VLAN 20. Even though they are plugged into the same switch, they can't talk to each other directly. So to communicate, traffic has to travel up this single physical link to the router. This link is a trunk. It uses 802.1q tagging to carry traffic for multiple VLANs simultaneously. The router then receives that traffic on sub-interfaces, which is virtual interfaces dividing that single cable, and then it routes it back down. This allows us to apply security rules like ACLs at the router level, ensuring that the HR data stays separate from the engineering data. And then next in chapter 9, we leave the local building and we enter the WAN, or the wide area network. So this is how we connect different organizations across the internet. This map perfectly visualizes the difference between interior and exterior routing. The clouds you see represent autonomous systems, or AS. These could be an ISP like Verizon, or even a large university campus. Inside those clouds, we use IGPs, or Interior Gateway Protocols, like OSPF. They're fast and know every detail of that specific network. But look at the connections between the clouds. That is the BGP, or Border Gateway Protocol. BGP is the glue of the internet. It doesn't care about the small details inside the cloud, it only cares about the path to reach the next autonomous system. It is slower and more complex than OSPF, but it is the only protocol scalable enough to handle the hundreds of routes that make up the global internet. Next, in chapters 10 and 11, we cover risk management and access control. As our architecture changes, our security must adapt. On the left, we need to distinguish between encryption and hashing. Encryption is a two-way street. If you have the key, you can lock the data, send it, and unlock it. We use this for things like VPN tunnels. Hashing, however, is a one-way street. Notice how the arrow doesn't go back. Once you hash a password, you can never get the original text back. This is critical for integrity. It allows us to store user passwords without actually knowing what they are. On the right, we have a modern solution for WAN security, which is SASE, or Secure Access Service Edge. Since users are working from home and accessing the cloud, the traditional corporate firewall doesn't work very well. SASE moves security to the cloud edge. It combines connectivity like SD-WAN with security functions like Zero Trust network access, ensuring that every user is verified before they touch any resource regardless of where they are located. And finally, Chapter 12 deals with performance and disaster recovery. We can have the best architecture in the world, but we must plan for catastrophe. This chart shows the trade-off between cost and time. On the far right, we have the cold site. It's the cheapest option because it's pretty much just an empty room with power. But look at the time curve. It takes weeks to recover because you have to buy and install hardware after the disaster hits. On the far left, we have the hot site. The recovery time is near zero because it's a real-time mirror of your network. However, the cost is massive because you are paying for double the hardware and licensing. Most companies tend to settle for a warm site, which is a middle ground where hardware is present, but data is only backed up periodically. In conclusion, modern networking is a balance. We balance speed with segmentation, accessibility with zero trust security, and recovery with budget. Understanding these trade-offs is the core of chapters 7 through 12. Thank you.